So we're going to take a look now at a collision involving a couple of beads, and you can see it says we've got 1.5 meters of height, so we got some potential energy also built into this problem. So we have a 0.4 of a kilogram green bead that slides on a curved frictionless wire. Okay, so frictionless wire means we can discount it. Starting from rest, okay, so initial velocity 0 at point A. At point B, the bead collides elastically with a 0.6 kilogram blue bead that is at rest. So B has velocity 0 at rest, okay? And this is going to be an elastic collision, just like we saw before. Find the maximum height. The blue bead then goes up the wire and stops. So that's the setup on the problem. Okay, so if we take a look at this, like I said, we've got a couple of we've got a boundary here that's happening. So we've got the first side we're going to solve using energy, okay? And then down here we're going to solve using momentum. And then we've got a head-on elastic collision, and then we're going to solve for energy as the potential energy goes back up. So we're going to be switching back and forth here on how we solve this type of problem. So we were given the mass of the first bead at 0.4 of a kilogram. Its height was 1.5 meters, and the mass of bead, the blue bead, was 0.6 of a kilogram. So we're going to start off by using conservation of mechanical energy. So we go back to our kinetic energy, potential energy relationships, initial and final. So let's find the speed of the green bead at point B just before it collides. So it's like we're going to take a snapshot as the green bead comes sliding down, and just before it kisses the blue bead and smacks it, we're going to stop the problem. Okay, it's like stopping the newsreel. Okay, so we're going to find the speed of the green bead just before it collides. So we're going to start with then our kinetic energy relationship. So you can see that's what we've gone back to, 1/2 mv squared mgy, all on the left side, 1/2 mv squared mgy on the side where the bead just before it hits. Okay, so we know that the initial velocity of the green bead is 0. So that's our first one we can throw away. But it still has all of the potential energy at the top of the wire. Then on the other side, we've got all of our kinetic energy as the bead comes sliding down, 1/2 mv squared. And at the bottom, just before it hits the blue bead, we have lost all of our potential energy. So that goes to 0. So all we're left with then is mgy A initial is equal to 1/2 ma velocity squared final. Okay, so again, this is one of those problems we can kill off the masses because the mass remains constant throughout that part of the problem with the green bead. So we're left with the acceleration of gravity times the height at the initial A point is equal to 1/2 the velocity A final squared. Okay, so now let's move terms around so that we have velocity A final, that's right there at the bottom, squared is equal to 2 times the acceleration of gravity times YA initial. So setting this up, taking the square root of both of those terms, velocity then A final is equal to the square root of 2G A initial, which equals 2 times 9.8 meters per second, 1.5 meters for the height that it started off. And that gives us the velocity of bead A final, 5.42 meters per second. So we've taken care of the first part of the problem where that bead is just about to hit bead B. So what we can say at that point is that the velocity of the bead then on the other side of this dotted line, the blue one, is now the velocity that A was. So it's going to give up. It's an elastic collision. It's going to give up its velocity A to B. So now, using conservation of momentum, we're going to start the projector again, and smack, green bead hits A bead, and we solve for momentum. So since the velocities then are the same, 5.42 meters per second, I can go back to my relationship for conservation of momentum. Mass 1, velocity A initial, mass 2, velocity B initial, is equal to mass 1, velocity A final, plus mass 2, velocity B final. And we can say that mass 1, velocity A, plus 0, because B at this point is still at rest, then is equal to A and B on the final side moving. Okay, so we have 4/10 of a kilogram. We have the velocity we just solved for, 5.42 meters per second. We have 40 kilograms times the velocity A final, plus 6/10 kilograms the velocity B final on the other side of the relationship. So now what I'm going to do is I'm going to divide through both sides by 4/10 of a kilogram, so that now I have 5.42 meters per second is equal to 4/10 of a kilogram velocity A final plus 6/10 of a kilogram velocity B final divided by 4/10 of a kilogram. And so now at this point you can see that we canceled out 4/10 and 4/10 on this side, but on this part it stays. Okay, remember your algebra. And I have velocity A final left. So now when I solve for velocity A final, I can get this far and I'm stuck. Okay, so I know that this becomes 1.5 times velocity B final. So that's as far as I can get on that problem. So I need to do something else. Okay, so the something else that I'm going to do is I'm going to solve for a head-on collision. So I haven't left this part of the problem. So velocity B final plus velocity B initial equals velocity A final plus velocity A initial. Velocity B initial at this point is still not moving, 0. And velocity A initial is moving at 5.42 meters per second. I told you this one was tricky too. So now, putting my values in, velocity B final plus 0 equals velocity A final plus 5.42 meters per second. I have velocity B final is equal to velocity A final plus 5.42 meters per second. So what I'm hoping to do here is get this set up for a substitution, possibly, that I can start solving one in terms of the other. Okay, so you notice I've changed colors here. The colors help me to keep track, so hopefully they're helping you too. So now I have 5.42 meters per second is equal to velocity A final plus 1.5 velocity B final. If we go back, there it is right there. Okay, so that relationship, now what I'm going to do is, since I solved for let's see, I have velocity B final, okay, right up here in blue. So velocity B final, I'm going to substitute for velocity B final here and put that into the relationship. And what does that do? That puts this whole expression in terms of solving velocity A final. So I'm going to multiply through and then start rearranging my terms. Okay, so when I multiply through, I get velocity A final plus 101.5 times velocity A final plus 5.42 is equal to 5.42. Okay, so I've just taken all of these terms and I've rearranged them so that I get velocity A final on the other side of the relationship. So I'll be able to factor it out here and factor it out there. So simplifying then, velocity A final, velocity A final times 1.5, 1.5 times 5.42, when I multiply this and this together, equals 5.42 meters per second. And now I can factor out my velocity A finals. I'm left with 1 plus 1.5 is equal to 5.42 meters per second minus the product of 1.5 times 5.42. Now that I have done that, I can move this whole term as a denominator on the other side of the relationship. So this will become what, 2.5, and I'm going to divide it into these terms. I can multiply these through and subtract them, and when I divide 2.5 into that, I will get a velocity A final of minus 1.08 meters per second. Okay, that's on this side of the relationship here, the model. So now, solving for velocity B final, I can take that value right up here, we're going to bring it down here, minus 1.08 meters per second plus 5.42 meters per second gives me a velocity B final of 5.34 meters per second. So that's going to be the velocity that the blue bead takes off, now going up the wire. Now, we go back to conservation of mechanical energy. Kinetic energy, potential energy initial. Kinetic energy, potential energy final. 1/2 mv squared mgy, 1/2 mv squared mgy. Initial, final. Now, I can start putting in my values of 0 at the bottom. The potential energy of the blue bead is 0, and its speed is 0. So both of those terms go away. I'm left with 1/2 the mass of the blue bead. Velocity squared of the blue bead initial is equal to the mass of the blue bead, the acceleration of gravity times y, the height final, which is going to be over here, YBF. Simplify by getting rid of the masses because it's the same bead. I get 1/2 v squared b initial is equal to the acceleration of gravity times the height. The height then, YBF, is equal to velocity squared bead B initial divided by 2 times the acceleration of gravity, and I get a height of 0.960 meters that the blue bead goes up the wire. Okay, so a long problem, but you can see how we had to cut it up, and we keep switching between conservation of mechanical energy and conservation of momentum to solve these as boundary value problems. So before we move on to the spring problem, let's stop one more time.